So this talk basically picks up topics that Petra already introduced and relates them to technical measures to realize these ideas, basically, or these laws. So I have also the panel in my way. Anyway, so the goal of this pipeline is basically to turn magnetic resonance imaging data into brain network models. So from MRI data, we really can extract highly personal information. Like here, everything you see here is extracted from the MRI data of a living human being. So we can extract the scalp surface, the skull surfaces, the cortical surfaces, the exact anatomy and folding patterns of the cortex, the white matter architecture. We can then parcellate the brain and make abstract representations of this highly detailed information that tries to capture the essence of the brain network. So the input of this pipeline is T1 weighted MRI, T-fusion weighted MRI, optionally T2 weighted MRI, and functional MRI. And the output is structural connectivity, region-wise fMRI, functional connectivity, surface triangulations, brain maps, and protection matrices. So the TVB on EBRAINS cloud infrastructure makes use of an ecosystem of interoperable services. So it's a service-based architecture. And as we learned already, brain modeling requires personal data subject to GDPR. So in this shared architecture, we need to protect this data. And the measures we talk about in this talk is access control, encryption, sandboxing, and also automation. EBRAINS provides several core services like a file system, a wiki, knowledge graph, and also supercomputing backends. And these are all connected via RESTful APIs. And these can use to call services that are implemented in a variety of deployments. So we have web GUIs, we have container images, Python notebooks or Python libraries that can be used in Python code, and optimized codes for the HPC backends. And one of these core services, the supercomputing services, are federated under the Phoenix research infrastructure. It's a network of 6 European, or the 6 largest European supercomputing centers that offer supercomputing resources to the scientific community. And as Pedro already mentioned, the problem here is that openly sharing or processing human data on such a shared infrastructure can compromise the privacy of the personal data of the research participants. And this is because we really have fingerprints all over our body, not only at the fingertip. So every voxel, basically, of an MRI dataset or of an fMRI dataset, for example, could be interpreted as a subject identifying fingerprint already. So we've seen this already, even with very simple information or high-level information that can be extracted from functional MRI data, we can find out highly personal information like the fluid intelligence of a person, their life satisfaction, and so on. And yeah, as it was already shown, the data from the Human Genome Project, basically the names of the subjects was basically reverse engineered. So there are these genealogy websites where people can do ancestry research, and they just publish gene information, for example, from the X and Y chromosomes. And by just comparing this gene information, which is linked to surnames, to the last names, and comparing this with the Human Genome Project results stored in GeneBank, it was possible to reverse engineer basically the names of these subjects. And with this, one can do all kinds of mean stuff, obviously. So the European Union recognized the problem that comes with highly interlinked data processing systems and data storages, and has this protection regulation basically that shall protect these data from getting into the wrong hands. And as we already saw, the controller is basically responsible for to demonstrate that the processing is performed in accordance with this regulation. So the technical measures that such a cloud infrastructure should have should basically give the controller, or should make the controller still be in control. So the controller shouldn't lose their control over their data while it is in the cloud. And also there shouldn't be just coming new persons into contact with the data. So the controller should still be able to control the data, even if the data is processed on distributed computing systems, where the controller maybe not even know where it is exactly computed, and where maybe other people have also access to codes, to processing infrastructure. So the technical measures should be in a way that the controller does not seize control, basically. And as we already heard, pseudonymity is not an option, basically. We cannot pseudonymize the data. So we can also jump over this. So yeah, basically what the law is about is there must be adequate protection of the personal data, like data minimization and so on. We've heard this already, so we can save some time here and come now to the technical aspects. So the image processing pipeline is basically a pipeline of containers. So the idea is, like with BITS apps, so with the brain imaging data standard, there are many different apps, for example, that all should be interoperable, that should be directly usable on BITS data sets. And we extend this idea here basically by having a pipeline that should be plug and play, where you can just add or remove containers as you wish. So here we have, for example, something for structural processing, fMRI prep for functional processing, and then a container that brings the outputs into a brain network model format. So the pipeline basically works by a user opens a GUI, a web GUI, a website basically, where they can configure the pipeline. So they can select which containers to run, select parameters, and then the data is uploaded, and on the supercomputer, an orchestrator basically performs all the processing. So the data controller does not need to work directly on a supercomputer. This is all automatized in the background. And this automation also protects data, because this kind of workflow, basically there's no other human being that can interfere or come into contact with this data at any point in time, basically. And after the workflow runs through, the results can then again be downloaded. So such a workflow in general, computation in distributed systems has always the same risk for data privacy. So we are sending data around networks, so they can be intercepted during transit. The data exists on devices, so if someone breaks the barriers or the logical barriers of a device, they can access the data. Or if they impersonate a user, they can also access the data. So these risks we have always, and here we try to mitigate these risks with also standard measures, or the most important measures of data protection: encryption, access control, sandboxing, and automation. So encryption is one of the most important techniques for data protection. So the data becomes completely unreadable. It's completely encoded, and therefore it increases the protection of data enormously if it is always encrypted. No one can read it. No one can read out the personal information. Of course, there must be a time where the data is unencrypted, when it is actually processed. And for this time, then we need additional safeguards like sandboxes, for example. But for sending around the data, for example, or for storing them somewhere, it's very good if it is encrypted. So if it's good if the data is encrypted before it leaves the computer of the data controller, and also if results are encrypted before being returned to the data controller. And the keys for decryption, the secrets that are needed to decrypt the data, stay always in safe locations, basically, where they're not accessible by people who are not a data controller of the data. So access control basically realizes or addresses a problem that we have here with the shared infrastructure. If we would allow everyone to just access the account where the data is processed, then they could install viruses, they could snoop around and steal data from others. So we cannot do this. So here a web GUI, a web interface basically allows to configure the steps of a pipeline. So you can select the subjects, you can upload the data, you can select the number of CPUs and so on. You can select the parameters of the processing. Here exemplified a few parameters for fMRI prep, for example, and Matrix 3. And everything that happens after that basically is out of control of anybody. It's automated. No one can interfere anymore with it because it's in isolated areas, basically. In sandboxes. So sandboxes provide only a controlled set of resources, like in your iPhone, when you install an app, then it asks whether it may access other parts of the system. And this is the same principle here. So if data is processed in an environment where other people have access and it is unencrypted and these people are not data controllers, then we must protect this data, and sandboxes is the technique for that. So we have things like temporary file system namespaces that are invisible even from the host of the same Linux user account, and which are securely cleaned up when the last process exits. And by combining public key cryptography and sandboxing, we can come up with workflows basically that are fully automated, where no one can really interfere and no one seizes their control. So when a data controller authenticates, then we can start a sandbox on the supercomputer, and only in the sandbox a public key is generated, and the private key will always stay there in the sandbox. So the confidential data that will then be encrypted with the public key on the computer of the data controller can only ever be decrypted inside the sandbox on the supercomputer. No one ever can decrypt the data again. And same thing vice versa. The data controller has their secret on their local machine, and only they will ever be able to decrypt the result. So this is really a maximum protection, North Korea level supercomputing architecture to really protect the data. So now let's switch gears for a little bit. And after we have talked about data protection now, another aspect of these pipelines is reproducibility. So we have reproducibility, and these sentences that now come are really typical sentences. This is not exaggerated. This is sentences that we read and hear on a day-by-day basis. So for example, now I really need to get rid of this box, otherwise I cannot read it. Okay, now I can read it. So here, for example, returning to work later, we had a question: which were the final versions, the ones which should go into article? It is possible that we put the wrong version of some figures in the final copy. Or when we went back to the old software library to try and do it, we couldn't remember how the software worked and abandoned the project. Or unfortunately, from the paper itself, we couldn't figure out what parameters were being used. We spoke to the author of the paper, who replied, we forgot which parameters gave the nice picture you see in the published article and thought it was best to leave things vague. So these things about these problems about computational science were known in the year 1995 and published there, but since then no one really cared about it, and the problem still persists today. So we read this sentence very often: data available upon reasonable request. Or when I run it on my machine, it gives the following error. So we cannot expect that our code works somewhere else. Or what is the difference between data version 8 final edit and data version new final CSV? So there are minuscule details in a computational data set make all the difference, basically, whether it works, whether the research is reproducible or not. And if it's not, it's basically abandoned. So I think we get the point. Computational results, it needs to be ensured that they are reproducible. And since 1995, still the same problems are haunting us. And yeah, this is again why this is necessary, because people believe after the article is written, it's not a problem anymore. So the article is about computational science and scientific publication. It's not the scholarship itself. So the article is really just advertisement of the scholarship. The actual scholarship is the complete software development environment and a complete set of instructions which generated the figures. So not the article, not the nice pictures, but really everything behind that generates the figures is the actual work, and this must be reproducible. And therefore, this must all be published. So reproducible workflows, version control data sets. So we always know which version of a data set are we dealing with and what has changed. Then data provenance. This is the whole history of digital objects. We know where it comes from, what happened to it, who did which changes at which location. Nesting data sets in a hierarchy of modular units allow us to create an evolution of data sets from the raw data to the finally published figures, where we can really nest the entire work reflow and reproduce the entire work reflow. So all the data really from the beginning to the end must be linked and be retrievable and recreatable. And this widely used standards obviously help with such interoperability, and metadata and documentation are necessary in a machine readable format. So the human readable format is usually not enough. Continuous integration, if we have such a hierarchy of research and we recognize an error, which we will surely do, then we need to continuously integrate a correction for this error. So we need continuous integration pipelines that at a specific point of the pipeline, again, go in and change the problem. Then the data must be accessible, obviously, otherwise no one can reproduce it. And containers are a nice thing to make stuff more reproducible. So research data management means that we want to create, use, publish, share, archive, reuse, or destroy digital objects like code, raw data, process data, results, but also figures and manuscripts in a way that makes these digital assets findable, accessible, and reusable. We know this all. And yeah, containers are a nice way to make workflows more reproducible. So we see here in the Docker file, the recipe for constructing a container image. There's all the instructions that are needed to build up the environment, and then also the final code that was used. But this is not enough. And this is a point where Datalet can be very helpful. So Datalet is like Git for data. So we all know GitHub, where basically source code is tracked on a line-by-line basis. So we really know exactly which line was added or removed or changed. And obviously we cannot do this for data that is like a gigabyte large. And their Datalet basically creates checksums. So really every file is tracked and indexed. We know a checksum, we know the exact identity of the contents of a file. And with this, we can version control arbitrary large files and create a provenance tracking evolution hierarchy. And we can more easily share and obtain data and program reproducible workflows in a domain agnostic manner. And how does Datalet perform this magic? It just extends the logic from GitHub. So a Datalet dataset is just a normal directory, a folder that has some hidden folders where all this provenance information is automatically tracked and stored. So Datalet comes out with a very few commands. We have, for example, Datalet create, where an empty data set is created and saved, where the modifications are saved, where we can add commit messages where we specify what we did. We can explicitly track where we downloaded something, where we obtained it, and where it went. And this allows us really to form a hierarchy of data sets that are nested and modular, and allow also to branch out into different projects from the raw data up to the finally published figures with papers and figures. And this all makes use of the standard file system architecture of computers. So it's nothing complicated or convoluted. It's just normal directories that have two hidden folders where all this provenance data is stored. And with this, we can flexibly combine data and containers into a reproducible data set. Because we really record explicitly where we got it from, where it is now, and what we did to it. So with Datalet, we do not execute commands like copy file from there to there, but we always prepend Datalet run and a commit message to it. And we specifically say which files are going to be manipulated. And only these files will then be unlocked. So we cannot randomly overwrite things in our data and accidentally destroy some things, but Datalet really manages this and ensures that we cannot accidentally just delete stuff or change stuff that is not reproducible then afterwards. And the same logic can also be applied to container steps, basically. So really with the Datalet command, we specify Datalet run, then we say what we did, like analyze the iris dataset, and then we explicitly specify what is the input, what are the outputs, and only these outputs will then be able to be overwritten or writable on the file system. And we also know exactly, sorry. So I should wrap it up now. We know exactly where we got it from. And we can do the same with containers, basically. We get a commit hash. We get a sequence of commits, basically, where we know, and also we can branch out, like with GitHub, and go into different directions. And we know exactly, we can explicitly track the evolution of a project and reset a data set to historic state. We can add or remove or revisit individual steps or recompute individual results without needing to store them. So we can rerun all our recorded computations via this commit hash, and this even helps to reproduce and verify results. So even someone who doesn't know what they are doing there, so they only need to know the Datalet commands, basically. So domain knowledge is not really necessary to decide whether this step really produced results, or even a reviewer can see whether the same identical information came out after an atomic operation, basically. And we'll jump over this. I think I'm almost out of time now. This is just to show that the Datalet commands are very simple and generic and can be basically added to any kind of workflow. It's just a small set of commands, very similar to GitHub. Basically, it's just wrappers around GitHub. So if you would like to have further information, we have a preprint out, brain modeling or brain simulation as a service, the virtual brain on EBRAINS. And to wrap it up, so as a summary, TVB uses access control, encryption, sandboxing, and automation to protect personal data in shared environments. And the pipeline can be configured via a web GUI. Containers capture all software and environment, and Datalet captures all the inputs, the containers, and how the containers were executed to return fully reproducible data sets. And with this, I'm coming to the end. Thank you.